Anybody got a reaction, a summary? What was Underwood Dudley? What was he trying to say? What do you think? Somebody give us one thought.
A lot of the math we learn.
Say it again.
A lot of the math we learn in schools doesn't have a practical application in jobs.
I think that was a big part of it, right? He was basically calling out us math teachers as liars and trying to fool our students, right? I think at one point in there he says, we should not try to fool our students, and I've been guilty of that. Every math teacher is guilty of that. And I think everybody likes, when a student says, when are we ever going to use this, right? A teacher wants to give you a valid reason, a nice thing to use. Even though I know most of the time when people ask me that question, I know they're not really interested in when they're going to use it. They're just trying to get out and maybe do it or something. But yeah, he made some interesting claims, right? I mean, about engineers not needing calculus or whatever, not using it, let's say, not necessarily not needing it, but using it in their everyday jobs. A lot of story problems are contrived. Of course, the one I always think of is our snowmobile problem. The guy stranded in the snow trying to get to the gas station, and he's going to sit there and do his calculation while he's freezing to death, figure out exactly where he's going, kind of thing. Okay. So he says, is math necessary? So the title of the question is math necessary? And so, okay. So that was one of the points he was making. What else? What about the historical part of that? I always thought that was interesting too. The historical part, like students in the 1700s, most people in the 1700s, Revolutionary War time went to how much school? What did it say? Yeah, not even Algebra 1, not even algebra, right? The vast majority of people didn't even learn algebra at that point. Now we're 18 years old taking calculus. A lot of students didn't even go to school past 6th grade or whatever, right? Went right into apprenticeships and work for jobs. So. Okay, so then what about his larger point? Is math necessary, yes or no?
He said it's good for thinking, like it teaches you how to think.
Yeah, I think that was really the main gist. I mean, that's what I get out of it. Really, one of the reasons I always like people to read this is because, and one of the things I said to you the first week of class was, there's a lot of different reasons why you guys are in here. Some of it is just you've been good in math, and so you always took the next highest math course, whatever it was, and you advanced along with algebra in 8th grade, maybe, or whatever. This is next. You just keep going, right? Or maybe you want to be an engineer, you want to do something where you're going to need it, or maybe you just like to be challenged, or maybe you want the AP for your GPA, whatever. All good reasons. That's fine. But, he talks about that, especially in that last paragraph, where he talks about, there's nothing like math to where you can see the right answer, where there's a way of doing things that make you think logic. So in other words, I think when it comes back to what Dan was saying about the jobs, he's telling it. It was kind of written for math teachers, to be honest with you. I think he says, quit telling students that they need it for these jobs. It's more important than that, right? They need math for even bigger reasons than that. Make them think, to make you think, to make you, and what the textbook author is talking about is just one of man's greatest accomplishments. He was talking about calculus in particular, but higher mathematics, those discoveries. Maybe that's a valid reason to study. Okay, anyway, I think that's an interesting article. Always made me think I remember when I first read it. It struck me, and hopefully it was meaningful to you. All right, let's talk about the homework here a little bit. Very important section here, 1.4. Matter of fact, this next 3 days, 4 days, our next quiz will probably be next Tuesday. Next Tuesday is probably our next quiz. Okay, so we'll be coming off a 3-day weekend, but Monday won't be much new. It'll be wrapping up a lot of stuff. So we got a lot going on here this week. We're going to learn a lot over the next 3 days. This can be really fundamental stuff for us all year long. This idea of the derivative is a really key thing. Now, our book approaches it from a graphical perspective, so we're going to be looking at a lot of things graphically. over the next several days. Okay, and talking about a function and its derivative, and then into the second derivative as well, and looking at relationships and so forth. Okay, so very, very important to feel comfortable and get an understanding of this. Now, it's going to get confusing here. You know, a lot of stuff's going to get thrown at you, a lot of different interconnections and relationships and so forth. But we're going to gradually organize that and make that, I think, come together pretty well by the time we get done. Matter of fact, it's typically a good opportunity for a good grade, to be honest with you. I think this next quiz will be worth probably over 40, maybe 40-some points. So in a disclaimer, it's a little bit like we talked about that one problem where if you get off track, all of a sudden you miss a bunch of stuff in a row, right? So there's not a lot in between when we get to this stuff. Okay, so like I said, the vast majority of it's positive. You're gonna get those connections, and if you're not, you got to be honest with yourself. You got to come see me. You got to come in and get help. You got to come in and ask me before we get to that point. Okay, so one of the examples we had though was throwing the ball up in the air in this whole equation here, and then we did the speed limit law. The speed limit law, which basically said, you know, if you know how fast you're going, you know something about how far you went. If you know something about how fast you're going, you know something about how far you went. If you know something about how steep the slope is, you know something about how high or how low the graph goes. Right? That's what the speed limit law says. If you know something about the rate, you know something about the amount of the function. Right? If you know something about the profit per book that you sell, you know something about your total profit. That'd be another connection, another thing that the speed limit law is saying. Okay, what homework problems do you want to look at? 25, I'm guessing. The 32, and that with the graphs. For sure we want to be able to do those. Okay, because that really ties into what we're going to be learning all week with these graph connections. So we definitely want to look at those. Okay, what else? 42. Okay, we're going to hit 42. 41. Okay, we'll probably hit 41. 42 is the one where you had to put it into words.
It was like try to find rank the F prime and negative.
Or was that 41 you had to put into words? What was the one you had to?
41.
41. Okay, yeah, that one for sure. 42, I want to do both those. Okay. So last time we introduced this new notation called f prime of x. A lot of times we just say f prime. So a lot of times your book just uses f and f prime when it talks about functions. It doesn't put the of x, you know, the parentheses part in, which is fine. We know that there's some input, but it doesn't really matter. It's t or x. Those are the ones it usually is, but it doesn't really matter. If we're just talking about a function in general, we can just talk about it as the function f or the function f prime. Okay, so f prime of x is either, and it can be either one of these, they're interchangeable, the instantaneous rate of change. So if it's a story problem with units, you're probably thinking about rate of change, like velocity, miles per hour, dollars per pound, feet per second, whatever. So it's some sort of rate with units, and we're probably thinking that one. If it's just a graph of some function or some points or whatever, then we're probably thinking of f prime as slopes. It's the same thing. It's the same exact thing, slopes or rate of change, okay? All right, 14 and 15. I don't think anybody asked about those, but I want to talk about them real quick. So here you got a picture. You got this graph here. One of the things we're going to really do a lot today is calculating, or notice I have approximating these slopes, these derivatives. So understand when it asks for f prime of -2, what it's saying. Okay, there's two ways to think about it. One way is it's the output of the f prime graph. So if they give you an f prime graph, okay, if we have an f prime graph, or later we'll have f prime equations, then if I ask for f prime of -2, it's just normal function stuff. You put a -2 into that function. But a lot of times they ask you like this problem. They ask you for f prime of -2, but what graph do they give you? That's the f graph. So now what do they want? Now they're saying they want the slope of this graph at -2. So we come over here to -2, and they want that slope. So on our next quiz, you will actually have some problems where you will be sketching in a tangent line like this, okay, on your quiz, and what would be probably the best way to estimate that slope? Go back to Algebra 1. Rise over run. To me, it wouldn't be pick 2 points because you don't know 2 points. The only 2 points you know are this one. Now, if you want to find another one, if you say, okay, if I extend this out here far enough, and there's a point, right? And what I would do, to me, it's always easier to do rise over run if the run is what? If the run is 1. Okay? Now, this is an approximation, but what I would do is a slope triangle. So I'd go here, and I'd say, okay, that's... So this looks to me like it's going up over 1, and it looks like it goes up, I don't know, about 7 or 8. I don't know, what you guys have? You have something similar to that? For 14? Is that 14?
15.
That's 15. Why did I have 14 down? It's 14. 14 is the F prime of 0. Okay, I got it. So I just got it written down. Okay? Now, my answer book has 10. Okay? Now, and so I got that leaning a little too much this way. It probably should have went up a little higher. But here's what I'm going to grade. Here's how I'm going to grade it. I'm going to look at your tangent line, and mine was pretty messy there. If this was a quiz, if I was getting graded on it, I'd have been a lot more careful. Okay? So if I'm getting graded on this, I'd probably say, okay, here we go. Let's see, about... So I still don't think that's 10. That's pretty close. Maybe it does go up there. But I'm going to look at your tangent line, and I would look at kind of your slope triangle. I guess I am kind of leaning in there a little bit. And so I would look at that, and I would say, is that reasonable? If you draw a tangent line that goes like this, that's not going to be good. That's not a good tangent line, right? So there's a lot of leeway there. Okay, a lot of leeway there. But if all you have is a graph, you really can't pick 2 points to do your slope calculation. So just draw a tangent line, sketch a tangent line, do a rise over run. At 0, right here, so we're looking at something kind of coming down like that. So over 1 looks like it's down about 5 or so. Let's see what they have here. They have -6 in the back on that one. On 14, -6. Okay, that looks pretty close. -5, -6, something like that. Okay, so sketch a tangent line, and I always make it long enough. I try to make it long enough so I have an easy run to work with. Run of 1 is best if I can, but, because last thing you want to be doing is estimating with decimals or something, if you can avoid it. Okay, so that should be simple. Should be simple. That's a skill we want to have. It's because it shows we understand what this means. It means slope of a tangent line on the curve. So our next quiz and homework, today, you'll be doing some of that, okay? You'll just be just drawing in a tangent line, estimating the slope, okay? All right. But we also, and actually today, we're going to talk a lot about this. Today, we're going to be doing a lot of this. We're going to be doing a lot of actually calculating. We're going to pick 2 points close together. We're talking about zooming. That's the title of the next section, actually zooming in. Picking 2 points really close together. Of course, we already did that on the first day, so we have a head start in the next section, kind of knowing what's going on with that. We're going to look at 2 points really close together, and we're going to be writing down those slope calculations. So that's another way to do it. Okay, so here we go. Here's our speed limit problem. So this is 25. Did I skip any? Did anybody want to say anything before that? Question, anything before 25? 12. Suppose that f is a linear function, f of x equals 2 minus x. That one? Okay? 2 minus 5x. Explain why f prime is a constant function. Okay, so what is f prime again? So when we see f prime, right away we think what? Slope, right? Slope of f, right? Slope of f. Now what kind of graph is this? It's a line. Right? It would be a line that would be up here at 2, and it would go down 5 over 1. So it'd be something, I missed it, but whatever. It'd be like that. What is the derivative of this line right here? It's because the derivative is the slope, right? What's the slope? -5, -5, -5, -5, -5, right? The slope is -5 everywhere on this one. So unlike this graph where the slope is changing all the time, this has a slope of -5 all the time. So the derivative, so not only would f prime of 1 be equal to -5, and f prime of 2 would be equal to -5, right? I mean, f prime at any point would be -5. So we can actually write f prime of x is -5. Yeah. Yeah. And so that would be the f prime equation. All right. And what would that graph look like? What's f prime of x equals -5 look like? Horizontal line right down here. Now that goes to those problems you were doing with the velocities and stuff. Okay? If this was a position function, what would the velocity look like? Okay, we're going to get to that in a second. All right, good question. All right. So, see, and that's the key. This week, no question is too dumb. And if you don't want to ask it in front of everybody, ask it to me individually, whatever, because the worst thing is to let something that's just a simple concept, but for some reason you haven't grasped it, and to let that bug you for a long time. Usually if you just ask about it and you get it straightened out, you're like, oh yeah, got it. Okay, so ask every time. Okay, h of 0, 0. So I went ahead and drew a little graph here, and this is that speed limit law. You can recognize it. They tell you about h, they tell you about h prime, so you're at 0, 0. They tell you, what does this say when you read this? What are you thinking right away? Slope is less than or equal to -2. So what's that mean? Could be -2, could be -3, -4, right? I like to think in those numbers. So slope could be that, which means I could go down 2 over 1, or I could go down 3 over 1, or I could go down 4 over 1, right? But I got to go down at least 2 and over 1. So is it possible that h of 5 is less than or equal to -10, or is that a true statement? Well, how did we talk about that? We said if you go over 5, how far are you going to go down? At least 10, because the slope's -2. So you go over 5, you have to go down at least 10, but you could go farther, right? So h of 5 could be down here at -10, but it could be even lower. So it could be, so it absolutely would be less than or equal to -10. Okay, now that's the one we usually understand. Okay, now this is the one that throws us off. Is it true that h of 3 is less than or equal to 5? Absolutely. Not only that, h of 3 has to be less than or equal to what? It actually has to be less than or equal to -6. If we go over 3, which is an input of 3, then we know we have to go down to -6. So h of 3 has to be less than or equal to -6. Has to be. But isn't that less than or equal to 5? Isn't -6 or -7 or -8 or -9, aren't those less than or equal to 5? Yeah, they're not equal to it. And I know that bothers some people. Okay? But again, it's like saying everybody in this room, even including me, everybody in this room is younger than 60. Right? That's true. Even though it would, if you take me out of it, it'd also be true everybody's younger than 20. Right? Or whatever. So every answer for each of 3 is less than or equal to 5. No question about it. Okay? All right. So that was 25. That was a speed limit law one. This is 28. I don't know if anybody mentioned this one, but this is another speed limit law one. Oh, wait, back up. Car talk. Okay? I might ask you a question like this at car talk. So I was talking about this with slope. Now, remember we said f prime is slope or rate of change. Depends on the problem, which you might want to talk about. In this problem, it made more sense to talk about as slope. It was just a graph with points. Okay, but now let's talk about it in car talk. So now let's make that slope be a speed, a rate. And what's our x and y going to be? Let's use miles per hour for the rate. So what's my x going to be? X will be hours, and the y will be miles. Okay? So what does this say? We start at 0. Okay? And we'll we'll use up and down. We'll use north and south this time instead of east and west like we did Bismarck. So we're going to start at 0. That's like Bismarck, right? We're going to start at Bismarck. And what's this saying? Going to go south at least 2 miles an hour. But we might go 3 miles an hour or 4 miles an hour or 5 miles an hour, right? Less than or equal to -2. So it could be -3, -4. So that means we're going south at least 2 mile an hour, but maybe 3 mile an hour, 4 mile an hour, whatever. Could we, so what's this saying then? Not could we, but is it true that this, so what is this 5? Hours. So is it true that 5 hours later, we're at least 10 miles south of Bismarck? So let's put it all together. So in car talk, this problem would be, okay, we're going to go 2 miles an hour at least to the south. We're going to start at Bismarck. 5 hours later, we have to be at least 10 miles south of Bismarck, but could be farther south, right? Is it true that 3 hours later, we're less than or equal to 5? Now, where's 5? 5 miles north. What's less than mean in this context? South of there, right? Less than would mean south. So is it true that 3 hours later we're south of 5 miles north of Bismarck? For sure, because we have to be where? 6 miles south, right? We know 3 hours later we have to be 6 miles south, so we're definitely south of 5 miles north of Bismarck, right? Okay, so that's how we could translate this into the rate language. We already did it with the slope language, talked about rise more.
So for that second one, could you also say that you'll never be more than 5 miles north of Bismarck?
Yeah, because this is saying that 3 hours later you have to be less than or equal to 5, so you have to be south of 5 miles. So you could say, since you would have to be 6 miles south, there's no way 3 hours later you could be north of, or there's no way you could be 5 miles north, right? You have to be less than or equal to. Yeah, I would say it. That'd basically be another way to say it. Okay, all right, let's look at 28. Suppose that f of 0, 2, f prime is greater than or equal to 4. What can we say about f of 1 and what can we say about f of -3? So, f of 0 is 2. Again, I would plot this. So what can we say about f of 1? Well, that means if we go over 1, what do we know? We got to go up at least 4, which puts us where? So f of 1 has to be greater than or equal to 6, right? Because this is greater than or equal to 4. So we have to go up at least 4, but we might have went up farther. So f of 1 has to be greater than or equal to 6. And f of -3, so that's a little weird because we got to go backwards. But again, we go this way 3, we got to go where? We'd actually have to go down, wouldn't we? Because our line's got to go like that, right? So we could go down 12, which would put us where? At -10 down here, right? And it could be on that line, but it could be steeper, so it might have went down farther, right? So f of -3 has to be less than or equal to -10, right? So when you go backwards, that sign ends up flipping because, remember, this is greater than or equal to 4, so it could be steeper. So if it's steeper, that means that line's going to come back a little farther. If we were up here, that's no good because then that would give us a slope less. Okay. All right. So those are just a couple different takes on speed limit law. Okay. Let's talk about this section. You know what? Let's come back to this section here. That's so important. Let's talk about 41. All right. Let H. This is always very timely because it's not always the day after daylight savings time, but we just did daylight savings time, and this is talking about daylight hours on 41. So the hours between sunrise and sunset, which is basically saying daylight hours. So they say that H prime of 100 equals 0.05, and then they ask this other question. So interpret that. So in words, somebody take a crack at that. Because this is, I gave you one of these, we did one of these on Friday, and I think what I said was on our next quiz, there will be something like this. I will explain, I will give you a context with units, and you'll have to turn this into words. What do you think?
Like after 100 days, the time in between sunrise and sunset will increase by like 2 minutes.
Okay? Now the only issue, that's getting pretty good there. The only issue I'd have with what you said after 100, and then you said will increase by. We want to be more instantaneous than that. So on the 100th day. Now keep going. Say it again.
So on the 100th day, the time between the sunrise and sunset will increase by like 2 minutes.
0.05 hours, which is 3 minutes. I like converting that to minutes because 0.05 hours is a silly term to use, which we never use. It's 3 minutes, right? Times it by 6 is 3 minutes. So on the 100th day, there's going to be 3 minutes more daylight. This is the way it's often said. There's going to be 3 minutes more daylight than on the 99th day, right? Okay, that's a way, in real life terms, it's often talked about, okay? But I like how he said increase. Why is it an increase? Because H prime is, because this number's positive, right? On the 100th day, after January 1st, the amount of daylight, on the 100th day, the amount of daylight, there's going to be 3 minutes more daylight, right? And that's perfect. That's perfect. Okay? Now, saying that it's an increase is good. So the first thing he said would be okay. It'd been okay to say on the 100th day after January 1st, the amount of daylight between sunrise and sunset is increasing by 3 minutes per day, if you want to say it that way. I like that because that gets that rate idea in there, 3 minutes per day. Now, you're also saying per day, if you say on the 100th day there'll be 3 minutes more daylight than the 99th day, you're getting in that same idea per day, right, in a 1 day increment. Okay? Now, let's make sense of that. 90 days or 100 days, so that'd be like 3 months plus 10 days, so all of January, all of February, all of March, give or take. So we're talking about beginning of April. Are the days getting longer, right, during that time frame? It's increasing, okay? And so that's kind of what the next question gets into. For what values will H prime be negative? Well, what's it mean for H prime to be negative? The days are getting shorter, right? When's that start? Summer solstice, which is on June 21st. Summer solstice. So it'd be a matter of finding out how many days that was. So I don't really care if you get exactly, but you know, that would be, 5 months plus 21 days, 170 somewhere right in there. That'd be about, let me see what they have here. They have 171, between 171, 354, something like that. Okay? But between the summer solstice and the winter solstice, right, we've got the days getting shorter, so H prime would be negative. Okay? And so we can think of what a graph of this might look like. Hours of daylight, January 1. So what's happening on January 1? The days are getting shorter, right? And so you've got this graph kind of going down. No. Days are getting longer, my fault. Until, what we say, 171? Somewhere in...
Would the summer solstice be included, or would it not be included for,
Well, it varies. I mean, they have it included. So
the winter solstice would be included too?
Right. I think you would say at that point, that would be the change, right? That would be, to be honest, you would be okay doing it either way. I think they could include it, but usually what we're going to do is on a max or min, because that's really what that is a max or min. That's your longest day and your shortest day. Usually we don't include those in the negative. Because to be honest, at the peak, it's 0, isn't it? Isn't the slope 0? So technically, Now, if this said less than or equal to 0, then maybe include. But when we get into local max min and increasing, decreasing, you're not going to get in trouble with the included, not included too much. You'll see when we get to that. So this is going to be going up, 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 up. It's going to peak, up here somewhere, whatever. Okay. So it is just, remember, on January 1, it's just hit its bottom back here on what? What's the winter solstice? December 21st, right? It's only 10 days earlier. It is bottomed out, right? So it's just on its way back up, and then it's going to start leveling off somewhere. Now, where is that where it kind of starts leveling off? What date is that? No. Summer solstice is when it peaks. It starts going faster and faster and faster, and then it starts leveling off. What's that date? Spring equinox. March 21st. What point is that? What do we call that point? Calculus. That's inflection point. Actually, it is. There's an inflection point at the spring equinox. If you were going to graph the hours of daylight, it would look like a sine curve, and it's going to come down like this. It's going to drop, 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 and then it's going to do this, and that's going to be in the fall equinox, right, which is September 21st, and then it's going to level off, and that's where we're in right now, right? We're in that time of year where it's really starting to level off here. Not my graph's all bad here. I should have had my bottom should be before Christmas here, so that's not a very good graph. But anyway, you get the idea. Okay, so the summer solstice, the winter solstice are those highs and lows. Now there's another interesting. I always like to throw this in because it's always this time of year, and it's got an interesting explanation as well. So you guys, this is perfect. You guys are all facing east. Okay, so as we face east and we look at the sun, and the sun's rising, right? And the sun comes up in the east and sets back in the west, right? So if you were to track the sun, so that's what I've got drawn up there. So I'm looking this way is my east, and over here to the right is south, right? Okay, so as the sun comes up in the middle of summer, right? And we're headed east here, and the sun comes up. Where's the sun in the sky? Over here or over here? To my left or to my right? As the sun comes up, does it come up over here? Does it come up over here? Does it come up straight overhead? Where is it? It's over here, right? Why is it over here? Because we live in what? The northern hemisphere, right? We live in the northern hemisphere. Okay, we live in the northern hemisphere. So the sun is over here to our south, right? Now, during the summer, where is it? Is it like way over here, or is it kind of over here? Is it up higher or is it down lower? Some of you never thought of this, man. It's up high, right? It's up high. But in the winter, it's down lower, right? It's down lower. Of course, the days are short, right? It doesn't take, but that sun doesn't get as high up in the sky. It's farther over here to the south as it tracks along. Okay, so what I would like to do here is draw a picture. So here's the sun. So here's the sun as it's coming up in the sky. So we're looking straight east, and in the summer, the sun gets up here. And let's say at its peak, which would be on the summer solstice, right? It's at its highest, this one, as we're thinking of this, right? And at the winter solstice, it's at its lowest, okay? So that would be like down over here, like this, right? And then in between, there's this track, right, where the sun is at various times. Are you with me? You see what I'm getting at here? Okay, now, what do you suppose is going on here? So right now we are where? We're way over here, right? So that sun's pretty low in the sky. Now, we're at November 6th, right? We still have a month and a half till the summer, or till the winter solstice, okay? So, doesn't it feel like the days have been getting short pretty fast here recently? Now, they've been getting shorter ever since when? Since June, right? They've been getting shorter. So think about it. After June 21st, the days get shorter, but pretty slowly, right? I mean, do you notice much difference in the middle of July? Don't the days seem pretty long still, right? In late July, the days seem pretty long. And even early August, the days seem pretty long, don't they? But all of a sudden, then they're starting to get shorter, right? And all of a sudden, if you watch the weather at night in Channel 13 and they say the sunrise and sunset, you know what I mean? So now the sunrise is gonna be at 9:07, and then the next day it's probably still 9:07, maybe it's 9:06. Pretty soon they start chunking up, taking off minutes, several minutes, right, in the data. Like you're saying, 3 minutes per day kind of thing, right? All of a sudden those days are getting shorter by bigger and bigger amounts, right? So what's happening is, that's this part. See, that's that leveling off kind of thing, or faster and faster is in this steeper part. So it's kind of slow. It's going down slow, but then pretty soon it starts picking up speed, and then what do you get right in between here? Right about halfway in between, where are you at? If this is summer, so this is June 21st, where are you at right here? Right in the middle would be what? The equinox, September 21st, right? So all of a sudden, you get into September, now the days are getting shorter pretty quickly. And all through September and into October, they're getting shorter pretty fast. But now it's starting to kind of level off, right? Now, all of a sudden, we're getting into October, now we're getting into November, now it's starting to slow down again. Right? Now, the equinox, where does the term equinox come from? Equal. What happens on the spring and fall equinox? What's equal? No, what's equal about them? Daylight hours and nighttime hours are equal. That's what happens on the spring and fall equinox. There's 12 hours of daylight and there's 12 hours of darkness. Okay? And so that's equal. Okay? So the sun is so slowly fading to our south until we get at December 21st, boom. What happens? It starts going the other way. Right? And it comes back to here. And it gets to here on June 21st, and it goes back the other way. Remember we talked about throwing a ball in the air? Before it turns around and goes the other way, what's it got to do? It's got to what? Stop. The velocity got to be zero. It's got to stop before it comes back the other day. So what happens on the winter and summer solstice? The sun stops. Where do you suppose the word solstice comes from? What do you suppose sol is? Sun. What do you suppose solstice is? When the sun stops. When the sun stops. Now, it doesn't really stop. But if you think of it as that graph right there, that's what it's doing. Okay, it's kind of this connection of when it hits this peak, what's the velocity? What's the rate of change? What's the derivative? Zero. Big deal. Calculus idea. Solstice, when the sun stops. So that's what they mean by the sun stops. It stops going south and gonna come back getting long. Okay. I love that problem. I don't know if you can tell or not. All right, 42. 42. Excuse me. All right. Rank these in increasing order. So we got, I think it turns out they are in order already, aren't they? Is that right? No, they weren't. No, never mind. Rank them in increasing order. So what this is saying is we don't know what their values are for sure, but we can tell something about them. So right away we think positive, negative. So look at f of -3. So f of -3 means a slope right there. What is that? That looks like that's 0. Okay, so that's going to be in the middle somewhere probably. F of -2. That's positive. I'm not even going to calculate them right now because I don't really need to. All I need to do is rank them. So that's positive, but it's not real steep, right? It's not real steep. What about f prime of 0? Positive and pretty darn steep. What about f prime of 1? Negative, but not very much negative, right? Oops. Negative, but not very steep. And then f prime of 4. So the only one that's really close are these last two. This one seems steeper than this one. I'd say that one seems a little steeper than that one. So that one is negative, but a little more negative, so like -2. So wouldn't that be our littlest? So if I'm going to rank them, it's going to be f prime of 4. Wait, I'm on the wrong one, aren't I? I'm at 5. F prime of 4 is here. Oh, that's definitely steeper than that. Okay, so f prime of 4 is steeper than that one, so that would be more negative. So that's going to be your smallest f prime, your smallest slope. So f prime of 4, then that one. So f prime of 1 would be next. Then f prime of -3 would be next, because that's a 0. And then we got this small positive would be next, f prime of -2. And then the last one would be f prime of -1. Or f prime of, I didn't draw that right, did I? God, what am I doing? Monday. F prime of 0 is right here. There we go. That's positive, okay? That's positive, but it's definitely steeper than this, right? So that's the last one. You knew it, didn't you? You knew I did that, Chase. You had no idea? Well, that's bad too. All right, so this is the most positive. Of course, it's worse than I did it when I've been teaching for 20 years. But, all right. So, 47. No, I'm still going back to those graphing ones. Let's talk about this one here. Suppose that f of 1 is 5. Find the equation of line tangent to the graph at the point 1, 5. So, all right, this is our first attempt at this question. You're going to see it 100 times this year. We better get really good at it. But when they ask me, they tell me that f of 1 equals 5, and they want me to write the equation of the tangent line. Now remember, anytime we're writing the equation of any line, all we need is that right there, right? We need two things. What do we need? Slope and a point. Now what did they just give me? They gave me a point, so all I need is that. So I got that. They gave me the point 1, 5. They almost always do, right? All I need is a slope. Well, what slope do I want? I want the slope at 1. I want f prime. I want you to start getting used to this notation. I'm not going to use m anymore for the slope, right? I'm not going to use m anymore. Because our slope will always usually be as a derivative of something. So whenever they ask me to write the equation of a tangent line, I need those two things. I need a point, f of something, and I need the slope, f prime at that same point. So I need f of 1, I need f prime of 1. Well, they gave me f of 1. How do I get f prime of 1? Come in here and do that. Jace, come in here and do this. No. Fooled you. Why not? Because that's what?
It's the actual graph.
This is not the graph of f.
It's a graph of f.
It's the graph of f prime. Right? So I wanted to make sure we understand that. So we've been doing all these problems where we have the graph of f up there. If we want to get f prime, that's the slope of f, we would draw a tangent line in there. But this isn't the f graph. This is the f prime graph. So what do we want on the f prime graph? We just want that y back. F prime of 1 is 2. So f prime of 1 is 2. And there you go. There's the answer to problem 47. But that's why. Okay, so you got to be careful. Which graph are you looking at? F prime. If you're looking at the f graph, f prime would be the slope of the tangent line. If you're looking at the f prime graph, then f prime is the y value. Okay? All right. Let's go back, speaking of graphs then, let's go back to these other questions. Again, we don't always spend so much time on homework, but this is so critically important, these ideas on this one. Okay, so on 32, plus we don't have a whole lot going on in this next section. At least a whole lot new. So in 32, it says we have an object moving away from the origin at a constant velocity. So it's got to be a line, right? It's got to be a line moving from the origin. We have no other options of what that could look like. Okay, now you're supposed to draw a velocity graph and an acceleration graph. Okay, now remember this would be P prime, and this would be what? V prime or P double prime, right? Okay, now I think it's best to just think of the primes, think of slopes. The easiest way to draw graphs of derivatives is just think of slopes. Remember, the derivative is a plotting of the slope values. It's a plotting of the slope values. Think of the problem we just did, where the y value on the prime graph, right, is the slope of the original graph. So all we have to do here is we have to think, what's the slope, 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 and then we come over here and we plot it. Well, what's the slope of that right there? Give me a number, make something up. Definitely not negative. 2. You could have said almost any number to have been right except the negative. 2. What's slope? 2, 2, 2, 2, everywhere. So let's go over here and plot that. 2, 2, 2, 2, 2, 2, 2. Horizontal line. Gotta be. Gotta be a horizontal line above the x-axis. Gotta be a positive horizontal line. Can't be anything else. Why? Because that's and it said constant velocity, so you gotta have a constant. But again, you only have to get hung up in rates and thinking about velocity. Just take a slope. Slope of this, 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 slope of this. Plot that as y-values. Now we do the same thing over here. Doesn't this graph have to be the slopes of this graph? What's the slope here? So let's plot 0, 0, 0, 0, 0, 0. Horizontal line right there. So if something's got a constant velocity, it has no acceleration, so it makes sense that its acceleration graph would be at 0. Constant velocity would have no acceleration. Okay, now it gets a little trickier because we have some options. Because 35 said it moves to the right, then to the left. But it doesn't say how it moves. So, what's this graph got to do? And it doesn't even say it has to start at the origin. Let's go ahead and start it at the origin. What could be one example of where does this graph have to go? Got to go up. Moving to the right means it goes up. So couldn't it be like an upside down V? How many people drew that? Okay, absolutely could be that. But couldn't it also be an upside down parabola? Couldn't it have been that? Where it was changing its speeds. Now, and to be honest, what's really physically almost impossible about this one?
It has to accelerate.
It's going to have to change direction without slowing down, basically. To be a V graph, it's going to have to change direction without slowing down, which would be really hard to do physically. Okay? So to be honest, the more realistic one's the top one. Okay? But let's go with this one. So what would this graph look like if you drew? So now your graphs are going to be different here depending on what your first one looked like. So slope, what could be a possible slope on here? 1, 1, 1, 1, 1, 1, and then negative, no, now not 0, and this is going to lead into our next lesson. It's not 0 here. We're going to see why in a second. But then it's negative 1, negative 1, negative 1, negative 1, negative 1. So how would that graph look like? It would go here, and then what? It would go here. Like that. We actually say that the slope is undefined at a sharp point. The slope is undefined. It's not 0. You might think it's 0 like a peak. It's not. The slope is undefined at a sharp point. Like that. Now, what if we were doing the blue graph? Now that would have been different because what's my slope here? Give me an example of what my slope is here. 4, 3, 2, 1, 0, negative 1, negative 2. So what's this graph got to be? It's what did we say first? 4, then 3, then 2, then 1, then 0, then negative 1, then negative 2. Wouldn't that graph have to be that then? If your first graph was the blue one, your second graph would have to be that, be a line going down. Again, all you're doing is taking the slopes of this one and plotting them over here. All right, and then what about this one? What would be our red graph? What's your slope here? 0, 0, 0, 0. 0, 0, 0, 0. So that would just be this. Okay? Actually be a hole right there. And then what about the blue one? What's your slope here? Negative 1, negative 1, negative 1, negative 1, negative 1, negative 1. Be down here. Right? Be like that. Okay? Okay, got to quickly talk about this one. Moving away from the origin at a steadily increasing speed. Okay? Away from the origin at a steadily increasing speed. So it's got to be a concave up situation, doesn't it? And the fact that it said steadily is actually important here. Okay? So now, what would be my slope? So what would be an example slope here? Could have actually been 0 to start with, and then what? 1, 2, 3, 4, right? So 0. So Would it have to be a line though? It would have to be a line. Since it's at a steadily increasing speed, it's going to go 0, then 1, then 2, and it's going to go up in even increments. And so it actually would be a line. If they wouldn't have said steadily increasing speed, if they'd have just said increasing speed, then this one could have been concave. This one actually could have went up like this, or it could have went up like that. If it just said at an increasing speed, but didn't tell us how, then we don't know. We just know it would have been increasing. We just know the speed would have been increasing, but it could have been concave up, concave down, or straight. Since he said steadily, we know it would be straight. Okay, and then what would this one be? Horizontal, like 1, 1, 1, 1, 1. Okay, so we plot a bunch of 1s. Okay, so we have that because we know it's steadily increasing. That'd be the acceleration, steadily increasing. So that's what. Yes, sir.
Isn't 37 it's moving towards the order instead of away?
Oh, I read 38. Okay, so flip these. Thank you. So it'd actually be this, like that, moving towards the origin. I read away from the origin. Sorry, I must have read 38. Okay, there you go. So what's this one going to be? So what kind of slope? 0, -1, -2, -3, -4. So where's this going? Down. 0, -1, -2, -3, -4. And then what are these slopes? -1, -1, -1, -1, -1. There you go. So the blue is actually what we should have for 37. Okay, we just did 37 and 38. All right. So let's jot this down here. There's really not much in this section that we haven't already done. So that's one of the reasons I spent some extra time going over this stuff. And then I decided to hand out the quizzes. So I took a little extra time. So I apologize. I got as much work done. So section 1.5 is just saying, okay, so if we need to figure out the slope, we need to estimate the slope. So what do we do? So one way we did in this last section is we just have a graph and we just sketch a tangent line and we just estimate rise over run. So we just estimate the slope. Okay? So what do they mean by zooming in? So so in your homework, I think there's going to be times where they're going to say, I put the hats out here. I know I forgot to tell you to put them on. That's okay. We don't need to. So they're going to say zoom in graphically. Okay, so what they mean is literally zoom in. Now remember Appendix A, we had that problem where we had to zoom in. We talked about that where we zoom in at a point, you know, till the line looks kind of straight. That was, or I don't know, we talked about it. That was your Appendix A homework the other day. So you can literally, you got a place on a curve, you can literally zoom in until the graph looks straight, and then you can just pick two really close points. So you literally zoom in and say you want to do the slope at 2, so you pick 2 and 2.01, and you do a slope calculation. You do this right here, okay? So you plug in your y, get your y at 2 and 2.01, and you subtract the 2 and 2.01, you do a slope calculation. Boom, it's super easy. Or it'll say zoom in numerically. Numerically might mean maybe they just give you a table of values, or maybe they just give you an equation, right? Maybe, so we don't really need to literally zoom in. I think there's going to be some problems. They might say graphically, literally zoom in. Not a big deal. I mean, it's not like you have to zoom in to be able to get those 2 points. You just trace, right? You trace at 2, you can trace at 2.01, and you get it. So it's not like you have to literally zoom in till that line looks straight, but that's the idea. Okay, I think I have, matter of fact, I know I do. I've got it up here. Tomorrow I'm going to send you one of these documents for your calculator, but right here. So I'm literally zooming in. Here we go. Literally zooming in on this point right here. Okay, this point right here. Literally zooming in. Zoom in, zoom in. Look at these values. You can see how these values are getting closer and closer. So we literally zoom in on a very local area. Notice that this document is called local linearity. Locally linear means that any curve, excuse me, any curve when you zoom in is going to look straight in a really small window. And since we can only do slope on lines, it makes sense that if we get it so it really looks like a line, if we pick two really close points, we're going to get a pretty good estimate of that slope there. Okay, now remember, the tangent line technically, though, only touches the curve where?
That's
At one point. So when you zoom in, okay, always keep in mind, when you zoom in and pick 2 points, you're estimating the slope, because here's the tangent line. Okay, I've done it, I've made it not quite touch for emphasis here, but that tangent line is only touching the curve at 1 point. So when you pick a second point, and I don't care how close you pick it to that point, are you picking another point on that line? You're not. So you're doing 2 points here, you're not doing 2 points on the line, and the line's what we're trying to get the slope of, right? Well, we can never get a second point on that line. The best we can do is get a second point that's on the curve, but it's so darn close to that line, because if we zoom in, the points, where this line touches the curve, the points on the line and the points on the curve are just so close together, it just doesn't hardly matter. Okay, that's the idea. Okay, that's the idea. Okay, anyway, so we're picking 2 points on the curve to estimate the slope of the tangent line. That's what we're doing. So you're going to do a lot of that kind of calculating in your homework today, either off of tables or graphs or equations. You're going to be doing these calculations. Okay? All right. So, for example, right here, if I wanted to estimate f prime of 2, right? What might you pick as your 2 points?
1.9.
You might pick 1.9 and 2.1, and that would be fine. Just show your work. So write out this, right? Like that. Write that out, then put those values in. So 2.1 would be 6.41 minus 5.61 over 2.1 minus 1.9, and calculate that out and see what you get. Okay, so you're going to be doing some of those calculations. Pretty simple, right? But that's basically the idea. So we've learned about the idea of a derivative, and now we're saying how can we calculate it, but that's it. Zooming in, pick 2 really close points. Estimating, yesterday we did off of a graph, do a rise over run off of a graph, but today's is going to be more calculated. All right, so 1.5 homework on your grade sheet. 1.5 homework for tomorrow. Okay? Oh, and also the V. Excuse me. If you have, so this is why this is undefined. Because if you zoom in, zoom in, zoom in, zoom in on a V, on a sharp point, it will never look straight. It'll never become like a line. So we say that the slope here is undefined, f prime is undefined, and there's 2 main places where f prime is undefined. At a sharp point, and that's just what we're going to call it, at a sharp point. Here would be another example. Let's say you have a graph that comes up like this and then goes down like this or whatever. Anywhere you have this sharp point, the slope's undefined, and here's another place where you sometimes run into this. There's not a sharp point, but what would the tangent line be there? The tangent line could be vertical. You could get a vertical tangent line, okay? And then the slope is undefined there as well, okay? So a vertical tangent line or a sharp point, we say the derivative is undefined. Okay, and that's it. With that, you should be able to do the homework no problem.